Hi students, good morning. Today's point is a physical quantity and it is angular momentum. So write down the point, fifth point, angular momentum. Angular momentum. It is denoted by L. When a body is in linear motion, the body has a linear momentum or only momentum. And we know that momentum is also a very important physical quantity, not only in this topic, it is in physics. Similarly, when a body is in a rotational motion, the body has a angular momentum. And so angular momentum is also a very important physical quantity. And a question will be asked on this point is, derive an expression for the angular momentum. So write down this question and denote it as a VVIMP question. Derive, derive an expression, derive an expression for, write down this question, derive an expression for the angular momentum. Angular momentum, angular momentum of rotating body. This is our question, and we already know that its answer is expressed in similar way as that of the previous point. Consideration, diagram, notation, and main mathematical part, which is also quite similar as that of the previous point, torque. So only small difference in which the consideration is made similar, like that. Consider a body is rotating about an axis of rotation passing through any point O with a constant angular velocity omega. In the previous point it is angular acceleration. Now why in this point it is angular velocity? Because angular velocity omega is close to the angular momentum, and so here instead of acceleration there is a angular velocity. So write down this consideration. Consider a rigid body. Consider a rigid body is rotating. Consider a rigid body is rotating about an axis of rotation. About an axis of rotation. About an axis of rotation passing through point O, passing through point O with constant angular velocity omega. Now the diagram is also in similar way. this is a crossing point is O. First point is M1, velocity is V1, its distance is R1. This is M2, its velocity is V2, its distance is R2. Then this is a third particle, mass is M3, distance is R3, velocity is V3, and suppose that it is a last point having mass Mn and distance is Rn. And after completing this figure, draw the boundary and show the direction of rotation with angular velocity omega. Now our third point is notation, and it is also in similar manner. Let M1, M2, M3, up to dash, Mn are masses of particles, Prepare your notes while watching this video. Masses of particles and R1, R2, R3, up to dash, Rn are their distances from axis of rotation respectively. This is our third point. Now let us start the main point, fourth point, and it is a mathematical part. We know that it is quite similar when rigid body rotates, then each and every particle of the body is in UCM. Body is in UCM, and we know that the formula in UCM can be used in this main mathematical point. In this mathematical expression, we will first express the linear velocity of the first particle, then linear momentum of the first particle, and from the linear momentum, the angular momentum of the first particle will be calculated, and then angular momentum of second, third, and so on. And in this way, we calculate the total angular momentum of the rotating body. So our first point is linear velocity of the first particle, second point is linear momentum of the first particle, third point is angular momentum of the first particle, and then second, third, and so on, and their sum is the total angular momentum of the rotating body. So write down first the linear velocity of the first particle is. The linear velocity of the first particle is the linear velocity of first particle is the linear velocity of the first particle is the linear velocity of the first particle is. We know that V1 is equal to R1 into omega because V is equal to R omega in UCM. So here the formula V is equal to R omega in UCM is used, and therefore the linear momentum of first particle is here it is P1 is equal to M1 into V1 because P is equal to MV. This is the formula for the linear momentum, and therefore P1 is equal to M1 R1 into omega. Now therefore the angular momentum of first particle is angular momentum L1 is equal to R1 into P1 because L is equal to R into P. This is the important formula, L is equal to R into P, from which we express the linear momentum of the first particle, and therefore L1 is equal to M1 R1 square omega. This is the linear momentum of the angular momentum of the first particle, and therefore or similarly angular momentum of second particle is angular momentum of the second particle is, we know that it is L2 is equal to M2 R2 square omega, and the angular momentum of the last particle is therefore Mn Rn square omega. Now from the first particle we calculate the angular momentum of all particles in the body, and therefore the total angular momentum of the rotating body is the total angular momentum of the rotating body is L is equal to L1 plus L2 plus up to plus Ln, and therefore from above expressions it is M1 R1 square omega plus M2 R2 square omega plus up to plus Mn Rn square omega, and therefore the common terms are M1 R1 square plus M2 R2 square plus up to plus Mn Rn square, and omega is constant, so it is not denoted as 1, 2, 3, and the compact form is I goes from 1 to N Mi Ri square into omega, and therefore it is I omega. This is our main expression. So write it as this is an expression for the angular momentum. This is an expression for angular momentum. In this way we completed today's point.